Hello everybody. Today I want to explain about the structure and evolution of stars. Let me share my screen. Yeah. We have the binding energy of the atomic nucleus. The general description of a nuclear reaction is, as you see, I plus J goes to K plus L and vice versa, where I is the baryon number and so the I is the nuclear charge. The nucleus of any element is uniquely defined by the two integer I and Zi. Recall that in any nuclear reaction, the following must be conserved: the baryon number and the lepton number and the charge. Note that the antiparticles have the opposite baryon lepton number to their particles. The binding energy of the atomic nucleus. The total mass of a nucleus is known to be less than the mass of the constituent nucleons. Hence, there is a decrease in mass if a companion nucleus is formed from nucleons and from the Einstein mass energy relation E is equal to mc squared. The mass deficit is released as energy. This difference is known as the binding energy of the compound nucleus. Thus, if a nucleus is composed of Z protons and N neutrons, its binding energy is Q, is Z plus N Mn minus M C squared. For our purposes, a more significant quantity is the total binding energy per nucleon. We can then consider this number relative to the hydrogen nucleus, as you see Q, Z, and N over A. The binding energy per nucleon. The variation of binding energy per nucleon with baryon number A. General trend is an increase of Q with atomic mass up to A is equal to 56, that is related to iron, Fe. Then slow monotonic decline. There is a steep rise from hydrogen through hydrogen 2, helium 3, to helium-4. Fusion of hydrogen to helium should release larger amount of energy per unit mass than fusion of helium to carbon. Energy may be gained by fusion of light elements to heavier up to iron, or from fission of heavy nuclei into higher ones down to iron. Here you see the abundance of the sun. Here it is element atomic number, and here abundance in atoms. As you see, we have hydrogen and then helium, and then we do not have iron. And then we have oxygen, carbon, nitrogen, other elements, and then iron. So we have mostly have hydrogen and helium and then oxygen, carbon, nitrogen, NEMG, silicon, and then iron. And if we have lithium and beryllium, it seems that they are we can find them in young stars. Here you see the binding energy per nucleon. Here you see fusion and then fission. We have fusion until iron, and then it declines and goes to fission into other elements, heavier elements. And fusion means two different species diffuse to higher species. as you see. And then for fission, we have, it means one element split into two different other elements. Coulomb barrier. Here you see this formula, and it is the energy required to overcome Coulomb repulsion and bring nuclei into contact. In this formula, ZA, ZB is the number of protons in each nuclei, and Ra plus Rab is the interaction radius. Epsilon 0 is the permittivity of free space 8.85 cross 10 to power minus 12 c square n minus 1 m minus 2. E is the charge of electron charge. DT reaction is VSC is or the speed of C is 0.38 mega electron volt. Gas temperature of 4.4 cross 10 to power 9 Kelvin. And here you see deuterium, and here we have tritium. Coulomb barrier. And we can say estimated temperature in the core of the sun is 10 to power 7 Kelvin. It is where the magnetic field hits the atmosphere of the sun. But here we have 10 to power 9, it is far away from our sun. Hydrogen and helium burning. The most important series of fusion reactions are those converting hydrogen to helium, hydrogen burning. As we shall see, this dominates approximately 90% of lifetime of nearly all stars. Fusion of 4 protons to give 1 helium-4 is completely negligible. Reaction proceeds through steps involving close encounter of 2 particles. We will consider the main ones, the PP chain and the CNO cycle. The PP chain has 3 main branches called the PP1, PP2, and PP3 chains. Maybe you ask when, how we can know that we have a PP chain in our sun. For example, when or which PP chain is ongoing on the sun. We can say when we know the flux coming from the sun, or we can measure the flux coming from the sun and then binding energy, then we can compare them. And for comparing them, we need the mass of the core. Then we can know which PP chain is ongoing on the sun. We can measure how much hydrogen, helium diffuse each second to produce the flux that we see. Here we have relative importance of PP1 and PP2 chains or branching ratios. Depending on conditions of hydrogen burning, T, rho abundances, the transition from PP1 to PP2 occurs at temperatures in excess of 1.3 cross 10 to power 7 Kelvin. Above 3 cross 10 to power 7 Kelvin, the PP3 chain dominates over the other two, but another process takes over in this case. Here we have PP1, PP2, and PP3 chains. Here we have the neutrino solar fusion. PP, this contraction goes to pp1, and then we have pp2, pp3, as you see in this diagram. The CNO cycle, or carbon, nitrogen, oxygen cycle. Remember that Z, or other elements in the sun, is less than 2%. Most abundant carbon, nitrogen, oxygen. CNO induce a chain of hydrogen burning reactions in which they act as catalysts. The process is known as the CNO cycle. There are alternative names in the literature. For example, the CNO bicycle, the CNOF cycle, the CN and NO cycles, the CN and NO bicycles, but we mostly call them CNO cycle here. The main CNO branch, as you see here, in the steady state case, the abundances of isotopes must take values such that the isotopes which react more slowly have higher abundance. The slowest reaction is P capture by nitrogen-14. Hence, most of carbon-12 is converted to nitrogen-14. Here we have CNO cycle for stars with M more than 1.2 solar mass dominant. And we can say for stars with M larger than 1.2 solar mass, we have more energy produced by CNO cycle than PP chain. PP chain is more in stars with mass less than solar mass. So we have a PP chain in our sun and CNO cycle for stars that have more mass than our sun. Helium burning, the triple alpha reaction. Simplest reaction should be the fusion of two helium nuclei. For example, helium-4 plus helium-4 gets beryllium-8. There is no stable configuration with A is equal to 8. Beryllium isotope beryllium-8 has a lifetime of only 0.26 cross 10 to power minus 16 seconds. But a third helium nucleus can be added to beryllium-8 before decay, forming carbon-12 by the triple alpha reaction. Helium-4 plus helium-4 get beryllium-8, and then beryllium-8 plus helium-4 get carbon-12 plus gamma. As you see here, also here. Carbon and oxygen burning. Carbon burning fusion of two carbon nuclei requires temperatures above 0.5 cross 10 to power 8 Kelvin and oxygen burning in excess of 10 to power 9 Kelvin. Interactions of carbon and oxygen nuclei are negligible, as at the intermediate temperatures required by the Coulomb barrier, the carbon nuclei are quickly destroyed by interacting with themselves. As you see here, 2 carbon-12 get oxygen-16 plus 2 helium-4, and so on. And 2 oxygen-16 give Mg24 plus 2 2 helium-4, and so on. The branching ratios for these reactions are temperature-dependent probabilities. Carbon-12 plus carbon-12 gives approximately 30 mega electron volt. Oxygen-16 plus oxygen-16 give approximately 16 mega electron volts. These reactions produce P, proton, neutron, and helium, which are immediately captured by heavy nuclei. Thus, many isotopes created by secondary reactions. Silicon burning. Two silicon nuclei could fuse to create Fe or iron 56, the end of the fusion chain. But now, very high Coulomb barrier at T above O burning, but below that required for silicon burning, photodisintegration takes place. Silicon disintegration occurs around 3 × 10⁹ Kelvin, and the light particles emitted are recaptured by other silicon nuclei. Although the reactions tend to a state of equilibrium, a leakage occurs toward the stable iron group nuclei, FeCO and Ne, which resists photodisintegration up to 7 × 10⁹ Kelvin. And you see here. Nuclear burning processes. Release of energy by consumption of nuclear fuel. Rates of energy release vary enormously. Nuclear processes can also absorb energy from radiation field. You see here nuclear fuel, hydrogen, helium, carbon, oxygen, and silicon. And you see the process of them, PP, CNO, and so on. And temperature threshold is 10⁶ Kelvin, as you see here. And products, outgoing and outlines, and then energy per nucleon, that is for a mega electron volt. And you see, when we have, for example, hydrogen, we have PP chain, and the product is helium, the temperature is low, but the energy per nucleon is high. And when it increases until silicon, that the process is NUC equation, and the threshold, temperature threshold is 3000, and the products is more and heavier, as you see CO, Fe, and Ni. The energy per nucleon is less. It is less than 0.18 mega electron volt. So the energy decrease, but the temperature increase, and the mass of the elements increase. The S process and R process. Interaction between nuclei and free neutrons, neutron capture. The neutrons are produced during carbon, oxygen, and silicon burning. Neutrons captured by heavy nuclei is not limited by the Coulomb barrier, so could proceed at relatively low temperatures. The obstacle is the scarcity of free neutrons. If enough neutrons available, chain of reactions possible, as you see here. If a radioactive isotope is formed, it will undergo beta decay, creating new elements. Here, if new element is stable, it will resume neutron capture, otherwise undergo series of beta decays, as you see here. We can have heavier elements by capturing neutron. Then we can have beta decay, as you see in these relations. The S process and R process, two types of reactions and two types of nuclei. One, neutron captures and beta decays. Stable and unstable nuclei. Stable nuclei may undergo only neutron captures. Unstable ones may undergo both. Outcome depending on the time scales for the two processes. Neutron capture reactions may proceed more slowly or more rapidly than the competing beta decays. The different chains of the reactions and products are called the S process and R process. And here you see them, the S process and R process. And here it is mass number A, and this is the elemental abundance, as you see here. Thank you for your attention and see you next time. Bye.